Hi everyone, today we're going to be doing integration by parts, and to do that we need to do a quick review of U substitution because that idea will be used when learning integration by parts. So let's get started. In this first example here we have 2x plus 5 raised to the second power, and we're trying to find the integral of that. So we need to assign our U value. U is going to equal the inside function, which is 2x plus 5. We take the derivative of that to determine what du is, which would be 2 dx. Once we look at that, we don't have a 2 dx in our original integral, so we need to divide by 2 on both sides to solve for dx. So that would be 1/2 du is equal to dx. Now I can replace everything in the original problem in terms of u. So that's what I'm going to do. So we're going to rewrite the integral. It's going to become u to the second times, and then our dx is replaced with 1/2 du. Of course, we can rewrite that to make it a little more friendly. You can put the 1/2 in front if you want, or you can keep it inside the integral, whichever you're more comfortable with. We're going to take the antiderivative of u squared, and that is u to the third divided by 3, which is the same as multiplying by 1/3. And now we need to put it back in terms of x and simplify our fractions here. So we'll get 1/6 times, and u is going to be put back to x, which would be 2x plus 5 inside. That's to the third power, and because our integral was not defined, we do need to have our constant of integration there. So our answer should be 1/6 times the quantity 2x plus 5 raised to the third plus c. Let's do the next one. So looking at this, we have the integral of x times the radical of 2x squared plus 3, and we need to do u substitution for this. So we're going to set the inside function equal to our u, so that'd be 2x squared plus 3 is going to be our u. And then we need to find the derivative of that, so that's going to be 4x, and then our dx on the end. Notice we have an x in the original integral, right up here. We have our dx, but we don't have the 4 that goes with it. So we need to solve for x dx here. So we're going to divide by 1/4. So, or excuse me, divide by 4, which would be the same as multiplying by 1/4. So we have 1/4 du is equal to x dx. So now we can start to replace. So our x dx will be replaced, and the inside function will be replaced in terms of u. So now we'll have the integral of, and I'm going to write this square root as an exponent. So it's going to be u to the 1/2 times, and then our x dx, remember, is 1/4 du. So 1/4 du, we can rewrite that. This time maybe I'll put the 1/4 out in front just to show you that it can be done both ways. So here we have our simplified integral. Now let's take the antiderivative. We're going to add 1 to our exponent here, so that'd be 3/2, and then divide by 3/2, which is the same as multiplying by 2/3. Okay, now we need to get it back in terms of x and simplify the fractions in front. So that is going to be 1/6, and I'm going to leave it as a exponent instead of putting it in terms of the radical. So that is going to be, again, replacing our u with what our x expression is. And don't forget your constant of integration on the end. Okay, so that is the review of u substitution. Okay, so having Done the warm-up, let's talk about integration by parts. So every differentiation that you have, your power rule, your chain rule, or your product rule, they all have a corresponding integration rule. So for instance, the U substitution rule that we just practiced for integration corresponds to the chain rule for differentiation. And currently, that's the only unique way that we know to help us work through some more difficult integration questions. Today, we're going to learn another way to work through some difficult questions. And the rule that corresponds to the product rule for differentiation is integration by parts. And that's what we're going to learn today. So here's the general idea. The product rule states that if f and g are differentiable functions, then the derivative of f times g is equal to, and this is what you already know, your first function times the derivative of your second plus your second times the derivative of your first. So that you learned in Calc 1. The notation for this, just think about this. So here's our original and we're taking the derivative. So if we were to take the integral of this, shouldn't it get us back to f times g? And so in other words, we're kind of putting an integral here and saying it should take us back to that f times g. And that's what this piece is over here, this f times g prime plus g times f prime. We're taking the integral of that and we're saying it should take us back to what we originally started with prior to taking the derivative, which was f times g. Okay, so now that we know the antiderivative of the result of your product rule takes you back to the original, maybe we should look a little closer at this integral and say, okay, well, there's kind of two pieces, this first piece plus this second piece. So let's apply the idea for integration where you can take the integral of each of those pieces separately. So this first piece and then plus the integral of this second piece. And that's what we've done over here. So we went from what's on the left to what's on the right. And we did that by separating our integrals. Okay, so now that we've separated our integrals, you can see that we have one piece plus another piece. But notice it's still equal to the original function. What we're going to do now is rearrange this equation here. And we're going to say, okay, well, this first piece can stay on the left, but what happens if I were to move this second piece and subtract it over? Okay, so subtract over. What you would get is this right here. Okay, so this new equation here is the integral of f times g prime is equal to f times g minus the integral of g times f prime. So you can kind of see parts of those product rules with the first function and the derivative of the second function. It's all interwoven there. It's just slightly rearranged. This piece that I just boxed in is the formula for integration by parts. Now, when you look at it this way with the f and the g prime and all that, it can get a little confusing because you're not really sure which piece we're talking about. So what they do is they like to rewrite it using u's and v's. So let's do that. F can be u, so the integral of u, and then g can be v, and because we're talking about a derivative, it's going to be dv. Okay, is equal to f again is going to be u times g, which is v, minus the integral of g, which we have as v, times the derivative of f, which would be u, so that's du. And this equation or formula here is the lovely simplified version of the integration by parts formula that you will pretty much need to memorize. My suggestion is to write it with each question that you do so that you don't get confused or accidentally mix up a u and a v. So start writing it when you're working through these questions, and eventually you will have it memorized. So again, like I said, it is easier to look at this in terms of u's and v's. And so this formula here is incredibly important, and that we will need to know. So the idea here is you're going to be given some sort of integral question, and you're going to have to figure out what part of this is u, what part of the integral question that you're being presented is u, and which part of it is the dv. And once you know that, once you determine what is u and what is dv, then this part over here is really just kind of like a recipe, okay? All right, so we need to know how to determine what u should be defined as and what dv should be defined as. And apparently, I didn't know this when I was going through school, but there's a neat little phrase called lipet, L-I-P-E-T, and I was told that a professor from the University of Delaware had come up with this. Not 100% sure on that, but that's what I was told. And LIPIT is an acronym for the order in which you should assign u. So if a part of your integral is a logarithm, you want to have that be what u is defined as. If you have an inverse trig function, that should be your u. If you have a polynomial, and by that I even mean just like a variable x is a polynomial, it's a first degree polynomial, that would be defined as u. Then you go to exponential functions, and then finally trig. So you kind of work your way down to determine what u should be defined as. And then at the very end, right down here, you do want to leave your dv as the messiest piece, okay? So dv should be kind of messy, but you want to have your u very nicely defined. So our u is going to need to be assigned. Okay, you're also going to have to define your dv. Oops. Okay, and then once you have everything defined and prepped, the integral on the right should be much easier to calculate and integrate. Okay, so that's kind of the idea. This is difficult to integrate the way it is. So by rewriting it using this recipe or formula, you're going to be able to integrate this integral on the right-hand side with much more ease. So this might be difficult, but the recipe or formula will help you get through it. Okay, so what's the process? The process is basically this. First, you need to determine what your u is going to be using LIPIT. The rest of whatever is in the original integral will be your dv. You'll figure out what your u, v, du, dv are, and you'll plug them into your integration by parts formula, and then you will solve. So it's generally the same process. As you go and practice these, some of them will be more challenging than others because you'll have to go back to some former integration techniques like u substitution to help you work through them. But we're going to start off nice and easy. All right, so here we have our first example. It's the integral of x times sine of x. And we know that we can't actually integrate this using any of the prior techniques we've learned. So that's why integration by parts is important. So the big idea behind integration by parts is you need to use it when you have two different kinds of functions that are multiplying together in an integral. So in this one, for example, we have a sine function that's multiplying, which is different than a polynomial, which is multiplying. So we have two different kinds of functions that are multiplying together. So the plan of attack is to use integration by parts. So we're starting with our integral of u dv. Okay, this is what we're being given. We need to figure out which part is the u and which part is the dv, but this is what we are starting with. And we know that once we know what u dv are, we can then use our integration by parts formula or recipe, which is u times v minus the integral of v du. But we need to first figure out which piece of our original is the u and which piece is dv. And again, that's when we're going to use the idea of limit. This will help you determine what your u should be. Okay, do we have a logarithm in here? No, so that's out. Do we have an inverse trig in there? No, we have a regular trig, but not an inverse. So that's out. Do we have a polynomial? Why, yes, we do. X is a polynomial, right? So just our plain X will tell us that, okay, we're good. We can stop going through Lipit, and we know that U is going to be defined as X. Knowing that U is defined as X, that's going to tell us that the rest of this, so the sine X dx, is going to be our dv. So dv is the sine of X dx. Okay, so now we need to use these two pieces of information to figure out their partner, so to speak. So u is equal to x, so the derivative of u, du, is equal to 1 dx, or just dx. Now, in this one over here on the right, dv, we need to take the integral to figure out what v is equal to. Okay, because we know dv, we need to figure out v. And to do that, you need to go backwards, because we're starting with the derivative and we need to go back to v. Okay, so just remember something that sometimes people forget. When you're taking the integral of dv, there's really like an invisible 1 there. So the antiderivative really is v. And that's why I want to point out, when you're taking the antiderivative of just that dv, there's really that invisible 1. And so it would become a v. All right? So we're not doing anything fancy there. We actually are taking the antiderivative. Nothing special is happening. All right, so now let's take the antiderivative of the sine of x, and that is negative cosine of x. Now, you don't need to worry about putting like a plus c on this yet. That'll come at the very end. Okay, so at this moment, we currently have ready to roll our u, our du, and our v. And that's what we're going to need in this second part of our formula. We need to know what u is, what v is again, and then du. So these three pieces are critical. So now what we're going to do is we're going to plug those in to our so-called recipe. So u and v will be plugged in first. So u is x, v is the negative cosine of x, minus the integral of v is the negative cosine of x, and then du is dx. So this left-hand side, of course, can be simplified, and this right-hand side we will need to take the antiderivative of. So let's keep going. So I'll take that negative and put it out front and have it negative x times the cosine of x. And the antiderivative of negative cosine. Well, first what I think I might do is write that as a plus, and then, so take that negative and kind of push it out in front. And then we can remember what the derivative is that gives us cosine. And the derivative that gives us cosine is sine. So the antiderivative of cosine is sine. Now we have negative x times cosine of x plus the sine of x. And now, since we're done, we're going to have that integration constant, and we can call it a day. All right, so that's example 1. So we're going to jump around a little in our notes, and we're going to jump to example 4. And so for this one, I'm just going to try and run through this one quickly. So it's u dv is what we're originally starting with. And we know we're going to need to use the integration by parts formula. Okay, so now that we know that, we need to figure out what u is equal to. So we're going to use Lipitz. Okay. And here we have ln. So do we have a log? Yes, we do. So we have the ln function. So that is going to be our u. And so now we need to figure out what our dv is. So if the ln is u, then really all we have there is dx remaining. And that is going to be what we set equal to dv. Now we'll take the derivative of u, so finding du. So the derivative of ln is 1 over x dx. And then we'll take the antiderivative to get to our v. So that's going to be x. And again, you don't need your constant of integration. We'll do that at the very end. So now that we have all of the pieces that we need for this formula part of things, we can plug it in to the integration by parts formula. So we have our u, which is the ln of x, times v, which is x, minus the integral of v, which is x, times du, which is 1 over x dx. So we obviously need to clean this up a little bit. You should put the x in front of your ln for the first part, so x ln of x. And then we can clean up the integral, so x times 1 over x is just 1 dx, or just dx. And so the antiderivative on that, of course, is just x. And then we need our constant of integration, since we have now done all of the integrals and we are at the end. So there's example 4. So something I want to point out is your answer can, in a way, be checked. This is, we started with an integral and we're going back to this expression here, x ln of x, I realize I forgot my x there, minus x plus c. If we take the derivative of this, we should really end up with what was in the original integrand up here. So the derivative of our answer should get us back to with what we started. So let's see if that actually happens really quickly. I'm doing it on this one because it's not such a time-consuming one to do this one. So if I take the derivative of x times the ln of x minus x plus c and figure out its derivative, so this first part we'll need to use the product rule. So first times the derivative of the second plus the second times the derivative of the first, and then the derivative of negative x is just -1, and then the derivative of our constant would just be 0. Okay, so let's simplify this. X times 1 over x is 1, plus ln of x times 1 is just the ln of x, minus 1, and then we don't need the 0. So the 1's would cancel, and notice what we're ending with, ln of x. And isn't ln of x what we started with in the original? That was the function that we started with. So that is a way to check if you ever feel the need. Okay, so now we're going to jump back to example 3. And I wanted to hold off on example 3 before because this one is a little more steps in actually getting to the answer, because you have to use some prior integration techniques in order to actually work through this question. However, this still starts the same way. We're starting with our integral, and we can see that we're working with two different types of functions. We're working with a polynomial t and a trig function sine. So we do need to use integration of parts for this. So they're giving us the original integral of u dv, and we need to use our recipe or formula, u times v minus the integral of v du, to arrive at our final answer. So again, we need to start with figuring out what our u is going to equal. And again, I suggest using the acronym LIPIT to help us. Okay, do we have any logs in our original expression here? No. Do we have any inverse trig? The answer is no. Do we have a polynomial? The answer is yes, we do. Our polynomial in this case is t. So we need to set our u equal to t, which means if t is equal to u, then the rest of it, sine of t dt, is going to be equal to our dv. Okay, so now let's figure out their partners. So u we have, so we need to figure out du. The derivative of t is just dt. And then for dv, remember to get to v, which is where we want to end up, we have to take the integral. So the integral of dv is v, and we'll also have to take the integral of the right-hand side, sine of 2t dt. Now, if you think about it, this isn't just an easy one to do. We have to use something special. Remember, u substitution. So we are going to have to change our variable up here because we already have a u and we already have a v. So they like you to use w. So I'm going to say w is equal to what's inside our sign, which is 2t. dw is equal to the derivative of 2t, which is 2 dt. And because I have a dt in my integral here, I'm going to solve for dt in this expression. So it's going to be 1/2 dw is equal to dt. So I'm going to rewrite this in terms of w. Okay, so kind of continuing down the line here, the integral of the 1/2 and the dw are there, and it's going to become the sine of w. All right, so the antiderivative of sine is negative cosine. So we'll bring that 1/2 with it, and it's going to be negative cosine of w, which now we need to plug back in terms of t. So it's negative 1/2 cosine 2t. Okay, so what we have here is we have our u, which we need for our by parts formula, our du, which we need for our by parts formula, and now we finally have our v for our by parts formula. So now we can go ahead and plug it in to find our final answer. Okay, so u is t, and that's timesing with our v, which we just determined was negative 1/2 cosine of 2t minus that same v, negative 1/2 cosine of 2t, and then we need our du, which is dt. Okay, so we have gone from our original t, sine of 2t, replace that with our u's and v's, and we now have this long expression, which we should definitely clean. So let's write that as negative 1/2 t cosine of 2t. I'm going to bring the 1/2 out and the negative out, so it's going to be plus 1/2 the integral of cosine of 2t dt. Now, I need to continue working on this integral on the right here because it's not just a simple one to do. We need to do u substitution again. And again, I suggest using a different variable, so I'll go back to w. So it's pretty much going to be a repeat of what we just did. So w is equal to 2t. dw is equal to 2 dt, so 1/2 dw dividing by your 2 is equal to dt. So kind of continuing down, it's going to be, oh, I need my 1/2 in front there. Okay, so we have cosine of w times our dt expression, which is 1/2 dw. And I'll move that 1/2 out in front, so it's going to be plus 1/4 cosine of w dw. And so I'm going to take the antiderivative of that. The answer to that would be sine. So it's going to be plus 1/4 sine of w, which would be 1/4 sine of whatever w was equal to, which was 2t. And then I need to bring down what was in front that I just haven't been writing yet. I'm just going to bring all that stuff down. So that is negative 1/2 t cosine of 2t, which was our uv part. And so this is our final answer with a plus c on the end. So notice in this, kind of reviewing the idea, you started the same way, but when you were trying to find the dv and the v pair, you had to use a u substitution in order to do so. When you plugged it in the by parts formula, the integral on the right wasn't as easy to do because you had to do u substitution on that as well. And once you do that, you will arrive at the final answer. Okay, so we're going to jump to example 6, which is going to involve inverse trig. We're starting with the integral of the inverse sine function, and that is going to be our u dv, and we are going to have to apply once again the integration by parts formula. But, like always, we need to start with determining what our u is going to equal, and we're going to use the idea of limit again in order to do so. So you need to ask yourself your questions here. Do we have any logs? No. Do we have any inverse trig? And this is the first time you've seen this type of example, and the answer on this one, of course, is yes. This one has the inverse sine. So I would suggest setting that as your u. So my u is going to be equal to the sine, so the inverse sine function. And if this is my u, then my du is going to be just the simple, or the dv, excuse me, is just going to be the simple dx. So now let's find their partner pairs here. So u needs a pair of du. So the derivative of inverse sine, hopefully you remember this, it's 1 over the square root of 1 minus x squared. And then, of course, to find our v, we have to take the integral. And if you take the integral of one side, you have to take the integral of the other, keep things equal. So the integral of dv is v. This one is nice and easy for us. The integral of dx would just be x. So now we have the important pieces. We have our u, we have our v, and we have our du. So we have all of the important pieces to use in our by parts formula. So let's go ahead and start plugging them in. So u is the inverse sine, and v is x minus the integral of v, which is x, times du, which is 1 over the square root of 1 minus x squared dx. And you know what I just realized I forgot to write on this? A dx. So let me add that on. I realized that I was remiss to write that. Okay. So now that I've plugged everything into my by parts formula, I need to simplify and reevaluate to figure out what the next step will be. So first I'm going to rewrite this first portion as x inverse sine x, okay? And then minus, I think I'll write the x on top here and write this as 1 minus x squared in the denominator there, dx. So I can see this integral is going to need a little bit of work. I'm going to have to use some u substitution. Again, we're going to use it as w substitution because we already have u's and v's over here defined. So I'm going to use w substitution in a way, and I'm going to set that equal to what's inside the radical in the denominator. So I'm going to write that as 1 minus x squared dw, the derivative of that would be negative 2x dx. And if you notice, we have an x in the integral by itself. We have the dx there. So really we need to solve for dx and an x. So x dx, and just move over that negative 2 through division. So negative 1/2 dw is equal to our x dx. Okay, so now that we know what our w substitution here is going to be defined as, and we're going to plug into this integral, let's really try and focus on this integral, rewrite it, get the integral portion done, and then we can bring it back to what we have here in the front, this x sine inverse of x. Okay, so let's just focus on the integral at this point. So we're going to have a minus the integral of, and now we're going to put it in terms of w, right? So we have our negative 1/2 dw to replace our x dx. So I'll put the negative 1/2 in front and the dw in the back. And then we have this radical in the denominator. Now you can certainly start with it in the denominator, but I'm going to bring it up as a negative exponent. And that exponent would be, a half because it's the square root. So negative 1/2 is how I'm going to write that. And again, instead of writing 1 minus x squared inside, we're going to write it in terms of w, so it's w to the negative 1 power. Okay, so now what I think I'm going to do is bring forward this negative 1/2, and so now it'll be a positive 1/2 integral w to the negative 1/2 power dw. Now I can integral of this. So I add 1 to my exponent, which would be w to the 1/2 power now, and then divide by 1/2, which is the same as multiplying by 2, or 2 over 1. So we're multiplying there. So this 1/2 times 2, of course, would really just simple out to be 1. And then you can write the 1 there or not, w to the 1/2 power. So let's get it back in terms of x, and we'll write that as 1 minus x squared to the 1/2 power. And then what we can do is bring down everything that was in front before that we just kind of had as like a little placeholder. Okay, so we're going to bring that down, and that was x sine inverse of x. Okay, so I'm going to write that as x sine inverse x. Okay, so we have x sine inverse x plus 1 minus x squared to the 1/2 power. Don't forget your constant, and I think we are good. Now you can leave that as a fraction exponent, or you can put it back into a square root. Whatever you prefer is fine with me. So that would be an example of one that does inverse trig. And this one did use a little bit of our prior technique for integration with u substitution, but we had a w instead. So that is an example of number 6. All right, now we're going to go to example 8, which is on the last page of your note packet. And you can probably see that example 8 has a lot of space underneath of it. And that's probably because it's the most complicated. And yes is correct. This is going to be the more complicated one. This is going to be an example of something that is cyclic. So it's continuing a behavior. So we will see what that means in just a moment. So you are going to need a bit of space on this, but just be happy because this is the last example in the notes for this video that you're going to have to do. So we are almost there. The process for this starts the exact same way we've been doing it before. We're being given an integral, e to the x times the sine of x. Notice these are two very separate functions here, so we're going to define this integral as our u dv, which means we need to figure out what u is equal to, and we need to figure out what dv is equal to. You want to start with what u is equal to using the idea of Lippitt again. And do we have a log function? No. Do we have an inverse trig function? No. Do we have a polynomial function? No. Do we have an exponential function? The answer is yes. We have an exponential function. It is e to the x. So that's what we're going to define as our u. U is equal to e to the x. So if u is equal to e to the x, then that means du must be equal to the sine of x dx. So dv is equal to the sine of x dx. So now we need to take a moment and figure out their partner pairs here. So u is equal to e to the x, so the derivative of that, e to the x derivative is nice, it's e to the x. Don't forget your dx on that. And then dv, remember we need to take the integral of both sides. And I just like to show this step because it really shows how you're getting that v. It's really showing you that, oh, I am taking the antiderivative. So I personally like to show that step. It helps keep me straight. So we're finding the antiderivative of the sine of x. And I guess I could have gone straight to the answer there. The antiderivative for the sine of x, we know, is negative cosine. So let's go ahead and write that in. So negative cosine of x. Okay, so knowing that, we know all of the important pieces. We know our u, we know our v, and we know our du. And remember, that's what we need in order to figure out the answer to this beginning integral. And that beginning integral is going to use the by parts formula to answer it. So uv minus v du. So this is our formula that we're going to plug in for. Okay, so let's go ahead and plug in. So our u is e to the x. Okay, our v is negative cosine of x. Okay, and then minus our v, which is negative cosine of x, times our du, which is e to the x dx. And I always kind of look at this and I'm like, okay, well, this is fine. I can very easily simplify this first part, just moving that negative forward. Negative cosine x e to the x. Well, that's actually kind of interesting. We still have an e to the x here, and we still have a cosine here. So notice we are still kind of not really that much different from where we started. So that's kind of odd. We're going to have to see what happens there. So we're going to keep going anyway and, simplify this first piece. So we'll put that e to the x forward with the negative. I'll bring this negative forward and make it a plus. And then maybe I'll move the e to the x forward too. So e to the x cosine of x dx. Now, unfortunately, in all of the ones that we've done so far, we haven't really had to do much beyond u substitution or w substitution to really simplify this remaining integral. But unfortunately, if you notice, we still are dealing with two very different types of functions. We're dealing with an exponential and then a trig. So we are going to have to do by parts again. And that is where you should be like, well, you can do it more than one time. And the answer is yes. Sometimes you have to do it multiple times within a function or within an integral, because it will continue giving you something like these two functions where you just have to continue doing it. So sometimes, yeah, you'll definitely need to go through the process of by parts multiple times or multiple rounds, if you will, in order to complete the problem. And so this is an example of that. So we're going to have to do by parts again. Okay, So, all right, well, I guess that means that I'm going to have to figure out my u again, right? And I'm going to have to use Lipit again. Okay, and let's see. Well, u and Lipit. Do I have a log? No. Do I have an inverse trig? No. Do I have a polynomial? No. Do I have an exponential? Oh, yes. Yes, I do. It's once again e to the x. So let's go ahead and write that down. So my u on this one is going to be e to the x. So that's my first part. My du, or excuse me, my dv. I think I keep saying du. I mean dv. So my dv here is going to be the cosine of x dx. Now I need to find their partner pairs, right? So my u's derivative is du, and the derivative of e to the x is once again itself. I'm going to have to take the antiderivative of dv, the antiderivative of cosine. So think to yourself, what derivative gives you cosine? And of course, the derivative that gives us cosine is sine. So this is going to be v is equal to the sine of x. So knowing that, I'm going to rewrite this piece here. All right. So let's do it again. Let me get some more space here. Whoop, a little too much space. All right. So I'm going to do by parts again. And so I'm just going to really focus on this integral piece. So this plus, and then it's going to be, remember, e to the x cosine of x dx is really our u dv. So that is the equivalent of our by parts formula. Okay, so we're going to be plugging it into this guy again. All right, so let's go ahead and plug in those important pieces. And again, I'll highlight those important pieces. So we need u, dv, and v. So we're going to go ahead and plug in. So our u is e to the x, and our v is the sine of x minus v, which is our sine of x, times our du, which is e to the x. And you know what I did again? I forgot to put our dx on it. So let me jump up there and do that. Okay. So I got to put that dx on there so that all my notation works out properly. And our integral here, so dx. Okay. What I did here is just cleaned it up a little bit. So I just kind of gave us a little space so that we can rewrite some things here. But I still just showed that we had to do by parts again on this integral, e to the x cosine dx. And I have all of the steps that we just went through. And the answer to that portion, that integral of e to the x cosine dx, is all the way here at the bottom, e to the x sine of x minus the integral of sine x times e to the x. So what I'm going to do is I'm going to write that right underneath, because this piece is the only thing we've been dealing with. This front piece, our u times v, is still there. So let's take a moment to write that down. So what we have is the front piece still. So that's equal to e to the x. Whoops, sorry, it's negative e to the x. Don't want to forget that negative. So negative e to the x cosine x plus, and then this whole integral's answer is way down here. Okay, so e to the x sine x, let's write that part first, e to the x times the sine of x minus the integral of the sine of x times e to the x dx. Now, is it okay with you guys? I prefer to write that e to the x first. So I'm going to take a quick change-a-roo and just switch the order. Okay, so I'm going to just put the e to the x first. Need my pen back. E to the x, and then put the sine of x second. Okay, so again, now we have our front piece from the step before. Then we have this e to the x sine of x minus the integral, which was from the second by parts. And we're still not done. Do you notice we still have an integral, and that integral is e to the x sine of x dx? But wait a second. Doesn't that seem really similar to what we started with? Well, in fact, it's the exact same thing we started with. So do you see how there's a cycle going on here? We started with e to the x sine of x. We did integration by parts. And the portion of the formula for integration by parts that gives us the integral got us something similar, but not quite the same as what we started with. Because we had to deal with that using integration by parts again, we did. And the portion of that that gave us the integral got us right back to the same integral that we started with. So there's a definite cycle. We can kind of see how this would go in circles. So we have to figure out how to deal with it. Well, the first thing you need to do is just write the full equation. So what is the integral you started with, and what do you now have? So let's take a moment and write that down. Maybe over here on the left is where I'll do that, okay? Okay, so we're looking at the full picture here. The only thing I did was I took the beginning integral, and I have that here, and I set it equal to our answer so far, which is right here. Okay? So we set those two things equal. Okay, so now that we know why they are set equal, I'm going to show you a neat way to deal with this cycle pattern that we have going on here. So if I were to continue to take by parts of this integral that we keep getting, we would keep going through this cycle over and over and over. So there has to be another way to deal with this. And in fact, there is. Notice that on the left-hand side here, we have e to the x sine of x in an integral. And on the right-hand side, we have the exact same thing. So you can kind of think of them as like terms here. And we're going to add over the integral. So that's kind of cool. We're adding over this integral on both sides. Whoop. Apparently I can't draw an integral symbol today. Here we go. E to the x sine of x dx. Okay. On the left hand side, those would add together, right? So we have one integral plus the exact same integral. So we actually have two of them. So 2 integral e to the x sine of x dx. And on the right hand side, of course, that would just cancel out. So what's remaining on the right hand side is that negative e to the x cosine of x plus e to the x sine of x. Okay. Well, the original question isn't asking what the integral of 2, e to the sine, or e to the x sine of x is. It wants to know what just one of them is. So if I take a moment and look back up here, I want to know what just one of them is, but currently I know what two of them are. So couldn't I just divide by 2, divide by that coefficient there, divide everything on the left and divide everything on the right by 2. The left 2's would cancel, right? And we would have remaining the e to the x sine of x, and I bet you know already where I'm going. And on the right-hand side, this whole expression is being divided by 2, which is another way of saying multiplied by half. So the question is, have we answered it? So here's that original integral, e to the x sine x. e to the x sine x. And do we know what it's equal to? Yep. Do we have any remaining integrals that we need to work with on the right-hand side? Nope. So we are good, and the only thing we need to do is add that plus c. And once we add that plus c, we have now found our answer, and it is 1/2 times the quantity negative e to the x times cosine x plus e to the x times sine x, and then our plus c. So when you see that cycle pattern developing, you need to work until you get back to that original integral there, and then use the idea of setting the two sides equal and solving for the original integral. Okay, so that is integration by parts. I do want to mention one more thing, and that is when you have a defined integral and there is, a theory behind them. So if we combine the formula for integration by parts with the idea of the fundamental theorem of calculus, you can evaluate a definite integral by part. And you would do so using this lovely formula here. Okay, so you can evaluate the u times v part of the formula at b and a, and then simplify your integral and evaluate that answer at b and a. Or you can, and I just added this in here, you can evaluate this whole answer to your integration by parts at the very, very end. Like here when we got the final expression, obviously without the plus c, you can evaluate it at the very end at b and a, but you have to just make sure that you're all in terms of the same variable. So if you had to do any sort of u substitution or w substitution, just make sure that you have it back in the original variable, and then you can evaluate it at b and a and subtract those two. So you can do it at the very end, and personally that's my preference. But just know that you can do definite integrals with integration by parts using the same idea, and you can do it at the very end, which is my preference. You can do what you want, but I prefer it at the very end, evaluating at B and evaluating at A, and then doing the subtraction. So good luck with integration by parts. Hopefully this video helped out, and we will do a little more in detail some other time.